high. So, we're going to learn about sound today. Alright, we're learning about sound right now because it is a form of wave. It's a compressional wave. Can you hear me now? Hope so. Alright, so all waves are made by something that vibrates, which means sound waves are also made by something that vibrates. When you talk, it's your vocal cords in here that vibrate. If you want to go ahead and play with that, you can, but please don't press too hard, you'll hurt yourself. Just gently touch your voice box and start talking. You'll feel the vibrations. Alright, sound waves are compressional waves, but you already knew that. And they need a medium. Now you know that. Oh, I should probably show you what you're doing at the notes. Let's see here now. Oops, sorry. Didn't mean to stick that in there. Let's put that right back over here. Oh, dang it. And that's not the notes. That's the notes. So, you filled in these blanks here. Sound speaks about something that vibrates. Sound waves are compressional waves and need a medium. Alright, back to it. Ooh. If it hurts your eyes, I'll move on. If it doesn't hurt your eyes, well, more power to you. Alright, what did I show you with that? I was showing you compressional waves going outwards from a central source. The matter wasn't going anywhere. Little dots weren't going anywhere. If you don't believe me, rewind, watch it for a little bit. You'll see, you can pick one dot and follow it. It just goes back and forth, back and forth, back and forth. It's not actually going anywhere. The wave goes out, the energy goes out, but not the matter. Alright, so what do all compressional waves need? Medium. Okay, answer it twice now. You should have the blank filled in. So the next pictures on your notes, picture of a couple of different types of two-wheeled vehicular transportations. Tells you, and for the analogy, the speeds of sounds. Sounds travel fastest through a solid. That's why for the solid I have the little, they call them crotch rockets, but whatever, the tiny little motorcycles that people use on the highways to weave in and out of traffic. Yeah. Sound travels not quite so fast through a liquid, and slowest through a gas. That's why the picture for the gas is a little moped. Alright, let me fix that. Something on my monitor that you can't see, but it's annoying me. There we go. Alright. So, knowing that, answer this question. Does sound travel faster or slower through a denser medium? Think about it. Pause, answer it, then come back and see if you're right. Here we go. Faster in a denser medium. Solids are denser than liquids. Liquids are denser than gases. Solids travel fast. I'm sorry, not solids. Sounds travel fastest through a solid, so sounds travel faster through a denser medium. How does that work? All right. There's not a section for this on your note sheet at all. If you want to write it down somewhere, you can. If not, hey, whatevs. It's totally up to you. Denser materials have molecules that are closer together. Closer the particles are to each other, it's easier to just transmit energy from one to the other. Think about it, it's a compressional wave, so particles, molecules, atoms, whatever, are being pushed into each other. If they're far apart, it takes them longer to hit the next particle. If they're close together, like in a solid, it happens pretty quick. Make sense? Good. Which travels faster, loud sounds or soft sounds? Think about it. Just think about it. The answer is neither. There it is. Loudness has no effect on the speed of sound. The only thing that affects the speed of any wave is the medium in which it is traveling. Medium controls speed. Nothing else controls speed but the medium. Okay, now back on your notes, it says increasing temperature means blank sound waves, decreasing temperature means blank sound waves. What's looking for either faster or slower? All right. So the speed of sound is controlled by the temperature of the medium. There's going to be a lengthy explanation. Take the word must out of that. I'm not in class to help you one-on-one. So just get through this and get to the answer to the questions, all right? Increasing temperature means faster particles. Faster particles hit each other more often anyways. Compression always move because particles hit each other. If they hit each other more anyways, the particles can transmit energy of the sound wave faster. Okay, summarize. Increasing temperature means faster sound waves. Decreasing temperature means slower sound waves. Okay, you've written those two words down, faster and slower. That's all you need to know. Let me give you an example. Some of you may have heard this before, or experienced this before. If it's a cold winter's day and you go to shout to somebody, you have to shout a little louder than you would on a warm day. Why? Remember, the sound wave as it goes out, it dissipates. The further away somebody is, the more energy you have to put into the sound wave to get them to hear you, to get the wave to survive long enough to get to them. But if the wave is traveling slowly, you have to put even more energy in it so it lasts longer, so you have to shout louder on a colder day. Not too many of you have experienced that, possibly because you didn't go out in cold weather. Those of you that are hunters have probably experienced this a lot, because during hunting season you go out at 4, some ungodly time like that in the morning, sit up in your deer stand or in your duck blind or whatever, and it's cold. All right. Properties of sound. So the first we're going to look at is loudness. The letter L was cut off there by the hole puncher, so if you want to fill in that L, feel free. Loudness is the human perception of sound intensity, which means I have to define the word intensity. So pause, write down the golden letters here, and come back to me. Intensity, how much energy a sound wave can push through a certain area in a certain amount of time. All right. This is the same thing as being more compressed. The medium is more compressed by the sound wave, which is the same as more amplitude. So on your notes, ignore the page 327 thing. On your notes, same as more amplitude. And I want to give you a couple of examples. Imagine you're back in my classroom, and I believe it's Mr. Taylor on the other side of the wall from me. The teacher, Mr. Taylor, not the AP, Mr. Taylor. If he's talking, doing his thing, and I drill a little hole, quarter-inch hole in the wall, and I stand there in the middle of my classroom, will I be able to hear him? Probably not. Maybe if I put my ear right up by that hole, I might be able to hear him then. Not a lot of energy is going through that certain area because it's a small area. But what if instead of him getting louder, I make the hole bigger, make it the size of a window? Will I be able to hear him then standing in the middle of my room? Probably yes. He's not getting any louder, but there's more area for the energy to go through. So therefore I'm getting more intense sound waves coming at me. And it appears louder. I perceive a louder sound. He's not making any more louder sounds, but my perception is of a louder sound. Another application, this little hole in the side of your head where the hearing happens, where all the wax comes out. Yeah, use Q-tips, but don't go too far in. There's a reason you have all this stuff here around it. This cartilage is called the pinna of your ear. It's to capture sound from a larger area and funnel it down to that tiny little hole. So instead of just hearing the sound waves coming in this tiny little hole, you catch the sound waves in this entire pinna, this entire area. Increasing the area increases the intensity, makes it easy for you to hear. You know, rabbits have really good hearing because they have these huge ears. Bats, huge ears compared to their body size. Okay, let's move on to the next one. So the relationship, I want you to understand this, between loudness, intensity, and amplitude is if one goes up, they all go up. If one goes down, they all go down. They're basically different ways of measuring the same thing. All right? Coffee. Alright, you need to understand that with distance, sound waves lose intensity. That's why I can't just talk like this and be a mile away from you and have you hear me. That's not going to happen. Not even 20 yards away from you. If I'm talking like this, you probably wouldn't be able to hear me at 20 yards. 20 times 3, which is 60 feet. You need to put more energy in there, more intensity for the sound wave to survive long enough to get 20 yards away from you before it just dissipates. How it dissipates is each collision between particles, you can read, converts some of the energy into another form. Every time you talk, basically, it makes the particles in the air shake a little more, which means you're basically increasing the temperature in the room every time you talk. And y'all complain about having a hot classroom. Well, stop talking. Anyways, if a sound starts off more intense, louder, it can travel further. Eventually, always run out of energy. I'm kind of glad sound waves run out of energy, because if they didn't, just think. What I'm saying right now, get out of my house. It will make it to your ears eventually. What you're doing right now will get out of your house and make it back to my ears eventually, so I hear myself over again. Every sound ever made would never stop if they didn't run out of energy. It would travel all the way around the world. And back again, because what's going to stop them? The world is round. There's no wall at the end of the world. It's round. Every sound you make going around and around the world forever, every sound ever made, still going around the world, that would suck. So, I'm kind of glad waves run out of energy. Especially sound waves. Alright, the unit for sound intensity is the decibel. Notice the little d for deci, the big B for bell. Big B means named after a dead person. Can y'all guess who? What famous person is named Bell? Person who eventually led to these things that y'all can't live without. Well, you probably could, you just don't think so. The guy who invented the first telephone? Alexander Graham Bell. So the decibel is named after him. He studied sound and transmission of sound over electrical wires. Alright, 0 decibels is the faintest sound a human can hear. 0 decibels is right down there. 120 decibels is the pain threshold. From that level of sound intensity on up, you're causing permanent damage to your hearing apparatus, the insides of your ears. Not this part, obviously, but the insides, the parts embedded in your skull. Yes, they can get permanently damaged. I'm not worried about page 329, don't worry about that. Okay, so here's a little chart. 20 decibels is the same thing as a quiet day in the country with the birds chirping and the bees buzzing by, and whatever. 30 decibels is a whisper right in your ear. 50 decibels is a normal conversation. 60 decibels is a busy office, or you could say it's a busy classroom if everyone's doing their job. Yelling is 90, a busy workshop can get up to 100. Rock and roll band get to 120. That's why a lot of those rock and roll band people go deaf over time. A jet plane taking off can get to 140 plus decibels. You don't want to be standing on the runway or at the side of the runway when it happens without some kind of ear protection. Alright, the next thing to worry about is pitch. So we're down here on the notes now. Please remember that has a P at the front of it, not a B. Pitch is the human perception, how we perceive things, of the frequency of a sound wave. You can pause, write that down, and come back. Do you remember frequency? How often a wave passes by? How many waves per second? Higher frequency equals a higher pitch, like that. I wasn't getting louder, I was just getting higher. You can do that too. Men have a falsetto voice. Lower frequency means lower pitch. Lower frequency. Okay, got that filled in on the notes? Alright, so Humans can hear sounds between 20 hertz and 20,000 hertz at birth. As we get older, we start losing this upper range quite a bit. And some of us are born without the ability to hear all of these. Some few people can hear above 20,000, some few people can hear below 20 hertz, not many. Me personally, I've tested myself around 13,000 hertz. I lose the ability to hear anything. It's a very high pitch. Some of y'all know that some of us teachers have this little app on our phone that puts out a very high-pitched whining noise that we can't hear because we're older. So put that in my pocket and walk around to the area where the kids all hang out and annoy them. Yes, I'm petty sometimes. But y'all shouldn't be hanging out. You should be going to class. Some of you are probably missing going to class right now, aren't you? There you go. Other animals have different hearing ranges, so here's a chart of that. Let me see if I can move my face out of the way. There we go. Alright, so humans from 20 hertz to, this is 10,000 right here, this is 20,000 hertz. The x-axis is a logarithmic scale, so we can fit all the data on here. Goldfish can hear from 20 hertz till about 2,000 hertz, about 1/10 of us. Cows, cats can hear way up there. Rats can hear way up there, but they ain't got the low end necessarily. Bats can hear way up there too, and beluga whale. Beluga whales are those medium-sized white whales, canaries of the ocean they're called. They make a lot of whistling noises we can hear, and they make noises we cannot hear too, but they can. Right, yes, tuna can actually hear, believe it or not. So can a bullfrog. Not much, but it can hear a bit. They can definitely hear each other. Alrighty then. Next thing is ultrasonic sounds. Ultrasonic sounds are sound waves of frequencies above what normally we can hear, so above 20,000 hertz. Alright, skip down to the infrasonic sounds. They are defined as sounds below 20 hertz. Alright. Now, made by, what can make ultrasonic waves? Bats can. Ultrasound machines in the doctor's office can, we'll talk about in a little bit, and dog whistles can. Some of the students have claimed they can hear a dog whistle. Okay, but you can't hear all of the dog whistle. You can't hear every single pitch it's making, just the lower ones. Lower for it, which is high for you. Alright, what makes infrasonic sounds? So infrasonic sounds are made by heavy machinery, earthquakes, and the wind. I don't know if the microphone's picking it up or not, but today the wind's blowing pretty hard outside my window and I can hear it whistling by. So it's making infrasonic sounds and sounds up above 20 hertz so I can hear it. Alright, pause if you need to catch up, and let's move on. The Doppler effect. Now if you look at your notes, oops, I don't want to do, oh, stop that. Stop that. There we go. You have Doppler effect here and Doppler effect here. Where are you going to write it down? I don't care. Taking your own notes, it really doesn't matter, does it? But if you printed out mine, you can write the whole thing here and then come here and look at the visual representations of it. Back over here. Alright, so Doppler effect is defined as a change in pitch, which is the wave frequency, or perception of wave frequency, caused by a moving wave source or moving observer, or both. Write it down. Pause if you need to. Come back. Here we go. So, I'm going to make a noise, and I hope it comes through across on the microphone. I'll check it out later after I'm done recording, see if it does. I want you to think to yourself, this is familiar or not. Sound like a car going by? I started off at a higher pitch, went down to a lower pitch. Why is that? Well, let me look at the notes. And basically, I imitated the second one right here with a stationary observer and a moving sound source. As something moves towards you, the sound waves will be closer and closer together because the source of the sound waves is moving towards you. So as each wave comes out, it's closer together. It's closer than it would have been if the source was stationary. They kind of bunch up in front of the source. If someone's coming towards you, those sound waves are closer together they're hitting your ears more frequently, you perceive a higher pitch. When it gets past you, they're stretched out. Because the source of the sound wave is moving away from you, each wave is further away from the next one than it would have been, and so they hit your ears less frequently. Lower frequency is a lower pitch. Same thing happens if the source is stationary and you're moving towards it and then away from it. Same thing happens if both the observer and the source are moving towards each other and then away from each other. What you need is relative motion. One has to be moving relative to the other. They both can be moving too. Alrighty then, let me move that out of the way. Some uses. Doppler radar. Doppler radar doesn't just tell us where rain is like a regular weather radar would. Doppler radar tells the weather person which way the rain is moving. Which means Doppler radar can be used to find tornadoes. Because when you have a tornado, you have a really tight little band there. Rain moving one way and then right beside it the other way as the thing is twisting around and around and around. They can see a tornado forming on Doppler radar and give warnings to people in its path. It's not perfect, but nothing is for tornadoes. They're too fast. Also, radar guns used to clock the speed of objects like baseball pitches and cars. Most of your cop cars, especially the Highway Patrol, has a radar gun built in. So yeah, see a cop car parked at the side of the road, make sure you're not speeding. Shouldn't be speeding anyways. And I believe that is the end of the notes. Yay! Alrighty. This in the middle. Excuse me, allergies. And let's make it bigger. Hey, there I am. Okay, so you have a worksheet. Skip section 3 on it, I think it is. Let me double check, make sure I'm not just BSing you there. But I believe it's section 3 I want you to skip on there. Now I gotta look it up. Move that out from behind me. I can't move that, can I? Oh, wow. Okay. Let's put that smaller. Now I can do it. Sound worksheets. Move me out of your way. Is it gonna open? And if it is, where did it open at? There it is. So section 1 is fine, section 2 is fine, section 3, skip this section right here. My answer sheet's going to have the answers on it. Alright, I'm not going to take my time to exit out or anything, but don't do it. You're not responsible for that. You don't have to. If you want to, knock yourself out. And then make sure you get this part and the rest of it on the last page there. Alright? Shrinky. Go bye-bye. Go bye-bye. Get bigger. And that'll be all till tomorrow. Have a lovely day.